anomaly detection using clustering methods and also by using the PYOD library. The PYOD library stands for Python Outlier Detection, and it is a comprehensive library for detecting outliers or anomalies. It supports a wide range of algorithms, including proximity based methods, clustering, and neural network. After installing the PYOD library and the Titanic dataset, we use the modules NumPy and Pandas for data modulation. We'll focus on the KNN clustering method here. We import the KNN model and we train the KNN model. We initialize the KNN detector and fit it to the training data. The PYOD automatically handles all the necessary computations. Once the model is trained, we can predict whether each point in the test set is an anomaly. PYOD provides a method called decision function that assigns a score to each point, where higher score indicates a greater likelihood of being an anomaly. Part 2. Now in this video, we look at DBScan using the PyCaret and the clustering methods. PyCaret is an open source local library that simplifies the process of training and deploying machine learning models. After importing the necessary libraries, we use Panda for data manipulation. We are working with the mice dataset. First, we check the shape of the dataset. Next, we process the data. Clustering algorithms like DBScan are sensitive to feature scaling, so we ensure that the features are normalized. Now we create the DBScan model. Using PyCaret, it becomes really easy to write this code. The DBScan model automatically fits a DBScan model to the data using its default parameters like APS and min samples. PyCaret abstracts away the complexity while giving us the control over the parameters if needed. Now we plot the model. The function generates a scatter plot showing the clusters identified by the DBScan. We also fine tune the parameters to improve the cluster detection and reduce the misclassification of outliers. Part 3. In this video, we'll explore document clustering. First, we pre-process and vectorize the documents. Then we perform k-means clustering. After using the k-means clustering and seeing the number of clusters, we visualize these clusters using the PCA components. When we use the k-means algorithm, it groups the documents into clusters by minimizing the variance within each cluster. Part 4. In this video, we look at the Gaussian mixture models clustering. We use the Seaborn library for this. The Seaborn library helps to generate 300 data points grouped into flow cluster with some overlaps, which is ideal for the GMM's capabilities. Next, we create and fit the Gaussian mixture model. This model learns the underlying distribution of the clusters. After clustering, we visualize the results by coloring each data point according to its predicted cluster. The scatter plot shows the clusters identified the GMM. Each color represents a different cluster. To measure the quality of cluster, we use the silhouette score. This metric ranges from -1 to 1, where higher value indicate better defined clusters. One unique feature of GMM is that it provides probabilities for each point belonging to each cluster. Part 5, Hierarchical Clustering. Clustering is a versatile, unsupervised learning method used to group data points into clusters. Hierarchical clustering creates a tree-like structure called a dendrogram. This structure helps us visualize how clusters are formed at different levels. After importing the necessary libraries, we generate synthetic data to demonstrate hierarchical clustering. The make block create clusters of points in a 2D space. The scatter plot shows a synthetic data with. To perform hierarchical clustering, we use the linkage method from the Skippy library. This method computes the distribution data points to form a hierarchy. While hierarchical clustering is powerful, it does have some limitations. It can be computationally expensive for large data sets. Outliers can significantly affect the cluster formation. In this video, we look at image clustering. Image clustering is a method of grouping images based on their content. Unlike classification, clustering is unsupervised, meaning the model finds pattern without prior labels. This technique is widely used in organizing image dataset, content-based image retrieval, and visual search engines. Here we are using a GitHub library called ImageBind. After loading the ImageBind library, we import an image from IPython. After instantiating the model, we load and preprocess the import, generate embeddings, print these embeddings and display images and play the audio. We also use the depth estimator function to get more enhanced features of the image. In this video, we look at k-means clustering from scratch. We load the Seaborn library. K-means clustering is an unsupervised learning algorithm that groups data points into k-clusters. The process involves initialization, that is placing k-cluster centroids randomly, assignment, assigning each data point to the nearest cluster centroid, and then recalculating centroids at the mean as the mean of assigned points. We repeat the steps until the centroids no longer change. We use the make-block function to generate synthetic data points grouped into clusters. The first step is k-means is initializing k-random centroids. Next, we assign each data point to the nearest centroid using the Euclidean distance formula. After assigning points to clusters, we update the centroids by calculating the mean of all points in each cluster. Now we combine this step into an iterative process. And visualize the final cluster and the centroids. In the last part, we look at the time series clustering. Time series clustering is an unsupervised learning method to group time series data based on the patterns of behavior over time. It is particularly useful in applications like detecting similar user behavior, grouping financial instruments, or analyzing sensor data. After importing the necessary libraries, we define the number of type points in each series and the number of time series. First, we ensure the time series is a 2D array before standardization. To get the features, we use features.reshape model to reshape them for clustering. We adjust the number of clusters as needed. Here we can see a visualization of the clusters formed.